Okay, so let's continue on here. So here can multiply that side, so it's 0.3 times 4 over 3, which is dy dt. So you know that 0.3, so 0.3 is actually 1 over 10. So this is 1 over, actually this is 3 over 10, actually this is 3 over 10 times 4 over 3. So this is dy dt. So here goes 1 time, so it's 4 divided by 10, which is 0.4. So this shows that the rate of increase for the y coordinate is 0.4 when x is equal to 1. So we have worked that. So I said I skipped the Roman figure 2 by mistake. So let's go to Roman figure 2. So this here they say find the equation of the curve. So need to find the equation of the curve. So how do we find the equation of the curve? So here we have dy dx equal to 12 2x plus 1 squared. So maybe you can do an antiderivative, derivative, which is actually integration. So we can do the reverse of a derivative so that you can have a function that is in terms of y and x. So we have a function, we get back the function that was where the derivative was performed. So because this is a curve, so now we need to find the integral of here. So dy, so we can multiply dx here, so it's 12 2x plus 1 squared. So this will be dx, so we can take the integral both sides and then add a constant. So we can pull out, okay, here when you do that we'll have y, so here you can pull out the 12, so y, so we can pull out the 12, so we have 1 2x plus 1 squared, so dx. Let's see. So okay, well, we can I don't know whether you have the special forms of integrals where you can use them, where I think it's something where there's a, let's say something like x plus c dx like this, and then you can they can maybe write what is the integral, so where you just pick the coefficients, say maybe something like this. So we pick the coefficients and then plug them and then get the integral. So maybe, but here the way I will do it, I don't know whether you, okay, from the way I look at it. So say you have, I hope if you have something like this, so this will give you ln x. So this is a special integral because you can't say maybe you know that 1 over x, you can write it as x minus 1, but when you find yourself having a problem now, this is not the same, because if you say negative 1 plus 1 divided by 0, which is not a very good thing. So it is known that this integral, actually you must know it by heart, that an integral like this is actually ln x. So natural log of x. So now if you have a form of an integral like this, x plus 1, so dx, so what you do here is that this would give you ln x plus 1. So you take this guy and put it inside here. This works when here we have a linear, so here must have a linear function. A linear function is a function of this form. So this is a linear function. You see that? So this will be a linear function. So when you have a linear function like this, you can perform the integral like this. But now here, yes, we have a linear function inside, but this guy. So if you can see, if you can have something like this, you can work the problem. So if you can let, so okay, so here, if you can have something like this, you can always find it. You can work the derivative of this. Maybe a function like this is not a linear function, so you cannot apply this way of doing the integral, of reading the integral. So we come up in a situation where this is not a linear function. So but you can have a trick in such a way that we can think of this as this, and you know that this is 3. Okay, you can work this integral like this. So okay, let me write the integral. So this is 12, this is 2x plus 1 dx. So here we can let a big X to be this part, so this part. So when you take a derivative of a big X like this, if you take a derivative both sides, so here will be 2 dx, here it will be 0. So then, because here you have this dx, so you need to substitute it, so divide by 2, so this will be something like this. So now you take this guy and substitute here. So y is equal to 12, the integral. So now in a position of this 2x plus 1, you put this bigger x. So this will be x, so this squared. And now instead of dx, you put dx over 2. So this is dx over 2. Alright. So and then you can take out the half. So this will be 12 over 2, which is 6. So this will be, so now you know that okay, you can write this like this. So now this is 6 times, so 2 plus 1 is -1. So -1 divided by -1. So y is equal to 6. Remember, this is a big X. So over X. So this is a big X. Remember that X. So X is 2x plus 1. So you need to substitute it back. So this would be -6 over 2x plus 1. So remember, plus a constant. So we're not done because we need to determine this constant. So this Remember, we have a point that we are sure is on this curve, which is the point P, which is 1,5. Remember, so we'll use this point to find what is C. So we put 5 here, so here we put 1, so it will be 2 times 1 plus 1 C. So this will be 5, so negative 6, so this would be 3 plus C. So here we have 2, so it's 5 equal to negative 2 plus C. So take this 2 that side, so it's 5, 6, 7, so it will be 7. So our C is 7. So now our final equation will be this as 1 plus 7. So this will be the final equation. Maybe if maybe to confirm, or to, I don't know how to put it, but if you can differentiate this back, if you can differentiate this, can we show that the derivative of this will give us dy dx, to check if our answer is correct? So let's do this. So maybe let's multiply this. So let's multiply. We can, okay, let's multiply. So, but I think okay, yes, we can multiply, but I think a faster way will be writing these like this. So it's negative 1 plus 7. So let's perform the the differentiation. So this would be dy. So here is negative 6 outside, so we take a derivative of this, so we drop the 1, then multiply 2x plus 1, then this would be, because we subtract 1, so this would be negative 2. Then we take the derivative of what is inside. So what is in derivative of 2x plus 1 is 2, and then dx. So derivative of 7 is 0. So now we have dy. So here multiply this negative in terms of negative, this will be 12. So this will be negative, power negative, so this will be over, this will be over 2x plus 1 squared. So this would be dx. So now you can divide dx both sides, so this will be dy dx is equal to 12 over 2x plus 1 to the power 2. So we got this derivative from differentiating the equation of the curve. So this proves that our equation is correct.